Hi, welcome to this video of another video of Singaporeans ramblings about nuclear technology. Yeah, okay, last time let me minimize this. Last time we were talking about uh, Schrodinger's equation, or at least the major implications of Schrodinger's equation. This is lecture 1 to 4. Now, this is the fifth lecture, so to speak. Um, and I wanted to um, give you a little bit more insight because I kind of rushed a little bit into the important effects of Schrodinger's equation without really and I skipped over a lot of detail. Now, just want to give you a brief idea where this detail comes from. Okay, if you look at this website called LibreText Mathematics, you will see where this Schrodinger's equation come from. You can see the math in all. It's for some of you horror, for some of you beauty. Okay, so let me roughly bring you through this. Okay, so mentioned before that the particles, okay, we were using this analogy of a guitar string. Where's this guitar string? So to go down a little bit. Yeah, here. The first picture of standing waves that we had was that of a guitar string. So you kind of fixed both ends tightly, and the wave can only vibrate within this point. So at either end, this what we call notes, these vibrations, there'll be like zero vibrations there. Okay, that's if you have the infinite ability to just keep both of these ends still. Okay, that's the so-called guitar string analogy. Okay, the guitar string analogy is what we call this particle in a one-dimensional box, okay, where we have over here infinite ability, or in this case we call it infinite potential well. That's the technical term. But basically it means that the the force field is so strong that there is zero vibration at either end of this so-called guitar string. Okay, so we like to do that, use this simplification because it is mathematically convenient to calculate, and it gives us the idea that energy levels are restricted. Okay, so it's what we call energy levels are quantized. These are allowed values. Okay, anyway, this just saying LibreText is free and open source, or rather free. It's this particular one is CC CC by 3 point BY 3.0, which means I'm free to share, copy, redistribute the material, adapt, transform or build material for any purpose, even commercially, as long as there's attribution. So credit to what's his name here? Jeffrey. Yeah, Jeffrey, for making this available. Okay, so basically what happens is that what's going to happen is that I'm going to give you lots of links and I'm going to put them as a typed document. As you see here, for example, I write relationship between energy, momentum, and wavelength. I put this Schrodinger equation right here. Maybe I'll put the URL here as well later on. Yeah, so all this will be in a typed document. So let me try putting in a URL here. Equals to let's see whether I can paste this here. Now I'm using Vim, NeoVim to be precise. And let's see whether yes, the thing is available here. Let's see whether clicking this will give you the link, and it does. So you can just hop over. I'm going to upload this in GitHub, or rather I'm uploading it now. Okay. Added Schrodinger equation reference, hit push. So basically what I've done now is just to upload it to Git. So you will be able to see these references available online. Probably write something a little nicer than this. Okay, so anyway, yes, that's the important equations that we must take note of the Schrodinger equation. So you can find it all here. Now, let me roughly go through how we think about a particle in a box. Rather, the particle in a box and move from a simple guitar string analogy to something a little bit more realistic. Now, I kind of glossed over it in the last few videos, or the last video, in fact. So it might leave some of you confused. So if you were confused, my apologies. I'll try to slow down this time round and slowly explain without going too much math. But unfortunately, the math is what gives us the basis for all these funny quantum behaviors. Okay, so remember our premise is that there's a force field. So this is the force field we're talking about. In this case, this force field is an infinite square well. Okay, the force field plus wave behavior will give us discrete energy levels. Now, why are these energy levels discrete? It's because of the equations, but behind these equations, what it means is that, okay, the momentum and the wavelength of a particle. Okay, this is a wave-particle duality, de Broglie, or de Broglie, I think it's de Broglie, I think. Pardon me if I'm mispronouncing it. Okay, particle wavelength and particle momentum are connected by this equation, and momentum and energy are connected by this equation. E equals half mv squared, and you change the momentum, P equals to mv. Okay, that is going to give you the correlation between classical kinetic energy and classical momentum. I say classical here because there's no Einstein theory of relativity here. Now, if all of that just flew past you, which I'm guessing it may because I'm intending this video set for non-technical audience, just know that energy, wavelength, and momentum are all interconnected and restricted. So in the sense that I was mentioning the last time, guitar strings, for the guitar string here, you cannot vibrate at any wavelength you want. Therefore, you cannot have any kind of energy or momentum you want. All of these are quantized. Okay, so this guitar string analogy works for some kind of basic understanding. Of course, this does not really reflect what is in a real atom, in a real nucleus, or in the electrons. So we sort of use this as a starting point to simplify our discussion. Now, the first simplification for this, now I'm going to start writing, and let's do what's this, annotations, lecture 5. Okay, so I'm going to do Schrodinger's equation again, or rather, I'm not going to go through the math, I'm just going to go through implications. So step 1 of understanding this is discrete energy levels. So we learned that from the guitar string analogy. Where you have a guitar string vibrating between two very fixed points. The technical name here is called the infinite square well. And it's a 1D, one-dimensional infinite square well. Means we only consider movement, or rather wavelengths along the x direction. Okay, 1D infinite square well. Now, the thing is that in a real atom, the infinite square well analogy doesn't quite fit. Okay? It doesn't quite fit because the so-called force field, okay, in this case, we have this force field. Hold on, something was rolling off. Okay, and I needed a break for a while. So anyway, I'm back. So I paused the recording. But anyway, this force field is infinite. Now, in real life, this is not going to happen. Force fields are not infinite. So let me put that in red. In real life, that's ugly. Real life, force fields are not infinite, or what we just call finite. That means they are limited, they have a certain quantity. So we cannot assume infinite force field. So let's have something a little bit more realistic. Finite force fields. Okay, this is gonna still, for the sake of the math, that's usually how it goes. For the sake of the math, we still keep it 1D, okay? And then we'll add little bits of complication all the way till we have something a little bit more realistic. Okay, 1D. Okay, so we have a finite force field, or what we call a finite square well, or finite well. Okay, so what is it here in this LibreText? In LibreText, the infinite square well is this one-dimensional box. Okay, but in a finite force field, we might have something like a simple harmonic oscillator. And what is this actually? So let me write that down. Simple harmonic oscillator. So let's have this point here. So your particle is around here. And let's say we push this particle away from this equilibrium point. And the force between this particle and this equilibrium point is basically the force of a spring force. So it's not a finite infinite force field, it's a finite force field. So that will actually give you this parabolic shape. Okay, this is the parabolic shape that we have here. At least that gives you somewhat of that shape, and it's a little bit more representative of a real life force field, such as the electric force field between electric force between a proton and electron. So that's a little bit of realism added in. So it's a finite force field. Okay. And finite force field means to say, yeah, for if you are interested, F equals to kx. This is Hooke's law, which you see here, Hooke's law. Basically, it means that the further you are away from a distance from this equilibrium point, the stronger the force of the spring. And this K is some constant that describes the stiffness of the spring. So this is what the simple harmonic oscillator is about. And if you push the particle here, it will tend to vibrate back and forth like that. Okay, so this is what the simple harmonic oscillator is like. Now, these vibrations will be very much like these guitar strings, as you see here. They'll be like these guitar strings you see here. I think I'm gonna draw that out for you. It is very much like these guitar strings. Okay, guitar string with an infinite square well. So, okay, we are gonna have our vibrations here. I'm not gonna draw it so nicely for you. Okay, so you have the guitar string analogy. Except now with Hooke's law, so to speak. With Hooke's law, yeah, your ends, okay, your ends here are not fixed anymore. And okay, so in the infinite square well, these ends are fixed. And they're fixed very hard. Okay, so this is the first picture that we were introduced to in this infinite square. Okay, there you go, much better. Infinite square well. Now, so if you have the finite square well, like this simple harmonic oscillator, What's the waveform going to look like after you do all the math? Okay, with a finite square well. So, well, basically what it's saying here is that the ends are given some freedom to move around. Okay, that is the so-called way I like to think about it. So you can still vibrate within these two points, but the vibrations do not get stuck within these two fixed points, but they kind of go outside a little bit as well. They spill over. There's a spillover effect. Okay, the spillover effect. Now just highlight it in red. Over here, there's a spillover effect. So if you were to draw a nice graph, you might have something like this. Okay, you have this you have these two bounds which are fixed. Okay, infinite square well. Okay, you will have these sort of vibrations where it's nicely fixed. Finite square well, it will start to leak up a bit. Okay, that's what the math says. Okay, that's wave behavior. Okay, so it will leak out a bit. Okay, so that the ends are, so to speak, they are not fixed. Okay, like this. Okay, ends leak out. Okay, and this is the consequence of the finite square well. Now, if you want to think of it in the guitar string analogy, you can, because in real life, okay, let's say you have a guitar string that's vibrating between these two so-called fixed points. In reality, if you have a guitar, okay, if you have a guitar with this fretboard, and I'm going to draw this here. Okay, so you have a guitar fretboard, and let's draw this nice thing. Okay, so between this point and you go all the way down here, there's only one guitar string, one bass string. Okay, bass guitar, whatever. Okay, let's just say there's one string. Now your fixed points of this so-called acoustic guitar, they'll be here. Okay, where these 2 points are so-called the fixed points. Now, the whole point of how the instrument, the guitar works, is that you strum this part, you strum this guitar string. That means you strum it. You strum this guitar string, thereby you transfer some energy from your hand into the string. So this string starts vibrating back and forth. And where do the vibrations go? The vibrations are supposed to travel down into this, of course it travels into the air around you, but more importantly, it travels through the solid here. Okay, it travels through the solid here into the body of the guitar, and the whole body actually starts to vibrate. Okay, so let's say the body is vibrating here. So I'm just going to put some effects down here. And once the body of the guitar vibrates, then it produces the nice sound that amplifies this guitar string, so to speak. Or rather, the guitar string energy transmits into this hollow body of the acoustic guitar, and the whole acoustic guitar vibrates. So in the sense, this guitar string in reality is more like a finite square well, because these ends have to vibrate. Okay, why do these ends need to vibrate? Is because you need to transmit some of that sound energy or vibration energy into the body of the guitar. Then you get your sound. So in reality, your ends vibrate. Okay? In reality, your ends vibrate. Your ends vibrate. Okay, and that's the only way you're going to get a real sound from the guitar. So in the quantum world, we do have these ends leaking out, they are vibrating out. And in this region, what we like to call this region is, this is where you have exponential decay. Okay, that's the mathematical thing, exponential decay. And if you see in the simple harmonic oscillator, you do have a little bit of that. Where's this exponential decay? Yeah, here's the exponential decay curve over here. So this is the EXP thing. If you're not sure, don't worry about the math. Just know that there's a mathematical basis. After you do all the math, there's a mathematical basis for why the waves leak out. Okay, so what do waves leaking out mean? Leaking out mean? Okay, so what I tried to explain before, is that these waves, matter waves, they're actually probability waves. Okay, probability waves. Right, so what it means is this, okay, for finite square well, let's say there's a finite energy. Okay, the particle has this energy E, or the wave particle thingy has this energy E. So traditionally it vibrates like that within the particle, but we just found out in a finite square well. So this is E and this is U. Okay, so U equals the potential energy. Okay, so the particle energy is less than the potential energy, but the potential energy is not infinite. So what happens is that, okay, instead of the waves vibrating like that, that's not the way. What happens is that some of the waves leak out. Okay, and maybe the picture I would draw is less of this. Maybe something like this would be nicer, because this is a little bit more representative of the nucleus. Okay, so again we have this leaky wave effect. Okay, and okay, it's gonna have an exponential decay here, and then it's still gonna like so-called go out. So again, E and U, where E is less than U. What does it mean? What do these waves leaking out mean? Okay, remember these waves called psi of x. These are sort of, or rather psi star psi, or psi x squared is a probability. Okay, probability of the particle being found somewhere. So if you have this wave leaking out effect, basically it's telling me that your particles can actually leak out of an energy barrier that is finite. Okay, so if the particle has maybe 1 unit of energy, and normally it requires 2 units of energy to escape, okay, or 2 joules. Let's say this E equals to 1 joule. That's the unit of energy. U equals to 2 joules. So you have a basketball that doesn't have kinetic energy. If it's a particle, it cannot escape. But because there's a wave nature to these particles at the quantum level, and you have this wave leaking out thing, you actually have particles that can leak through the barrier. Okay, particles leak through the barrier. Leak through the barrier. And what you're basically seeing here, some of you may already know, this is called quantum tunneling. So this is a strange effect that happens where a particle, normally with insufficient energy to escape some barrier, somehow escapes. Okay, so this is quite counterintuitive if you think about matter being in a particle form. But if you think of matter as a wave, it makes total sense. Or rather, the math tells you this should happen. Okay, so this is quantum tunneling predicted by Schrodinger's equation. Now, so basically, this whole finite square well thing is shown in this simple harmonic oscillator. And basically what it says is that particles can leak out, and that therefore quantum tunneling. Right? So that's the effect you get from having a so-called finite square well, quantum tunneling. Right? So where it may seem very abstract. Oh, what's the point of quantum tunneling? Okay, in the nuclear physics realm, it's very important for alpha decay. Alpha decay. Okay, or if you read even further, this is very important for fusion process as well. Fusion process in the sun. Okay, so basically what you have is so-called two hydrogen or two protons. These are called the hydrogen. They're supposed to come together, right? They're supposed to come together and fuse, but they do not have enough energy. But because of this quantum tunneling process, if you just bring them maybe close enough a little bit, the quantum effect starts to take over and they fuse anyway. Okay, they fuse anyway. Okay, so this quantum tunneling is actually pretty important because it allows particles to so-called overcome energy barriers because of this leaking through effect. And that is because of the finite square well, finite well, or finite energy barrier kind of a thing. So that's pretty important to note. And yes, this, so again, want to recap, because of the quantum nature or quantum mechanics, or rather, if you want to take away all the jargon, is the wave nature of particles, and because of the fact that you have force fields that restrict the movement, firstly, you will have the consequence of energy levels being fixed, or what we call quantized. And now, because of the wave nature of particles, and the fact that we hardly ever have infinite square wells, except maybe in a black hole or something, but we don't deal with black holes. Okay. Actually, I don't even know if a black hole counts as that. Okay, so scratch that. Okay, I think I'll let the experts talk about this more. For nuclear physics and chemistry, most of the time, if not all the time, we deal with finite square wells. And with finite square wells, your particles can actually leak out. Okay, your particles can actually leak out or quantum tunnel. Okay, so this is why people do all the math right here. Okay, so the particle in a one-dimensional box, this actually this tells you that they are fixed energy levels. Okay, the simple harmonic oscillator here, it tells you, because the force field is not infinite, that your particles can leak out. Okay, so finite energy well results in particles leaking out, aka quantum tunneling. Okay, so that's what you will get from running through these math exercises. So this is the first two parts. We have not even gone to 3D, so to speak. Okay, so I'll just stop for now. Hopefully you can sort of grasp the concepts without going through too much of the math, and I'll probably continue next time. Thanks for watching.